Good morning, my name is Ignacio Hidalgo. I'm going to present you the work titled Profile Glucose Forecasting using Genetic Programming and Clustering. This work is part of the PhD thesis work of Sergio Contador, also from our university, Universidad Complutense de Madrid in Spain. During my presentation, I will follow the next outline. First, I will give you some ideas about the final objective of this work as a part of a general project. Then, and also I will give you tool ideas about the problem in hand, that is diabetes mellitus, or simply diabetes. And then I will explain the methodology we follow to solve the problem of predicting the glucose values. And I will give a detailed description of the data collection, the pre-processing and division, how we perform the clustering of the data, and how we are using this for the training of the models, and then also how we select the best model with the Akaike criterion method. I will present some experimental results and the conclusions of future work. So we are dealing here with the problem of predicting the glucose values of diabetic patient. Diabetes is a group of disease that is characterized by a high level of blood glucose resulting from a defect or in the production or in the action of the insulin in the body. This is a real hard problem that affects today more than 400 people all around the world. So diabetic patients need to control the blood glucose level to avoid not only short-term complication but also long-term complication. The physician recommend to keep as much as possible the glucose level and healthy levels. Avoid the high and low levels because they are potentially dangerous. And for this, they use the concept of the time in range to know if the control of the glucose is correct for a patient or if it's not good. So the time in range is the time that the patient spends in the with level of glucose between 70 and 180 milligrams per deciliter in the day. So the higher the time in this range, the better the control. And the most dangerous situation is to maintain a high level during a long time, because this is very bad for the complications. The low levels values, especially the very low levels, are very dangerous because the patient can even die due to diabetic coma. So what the diabetic patient needs is to control this level of glucose. The patients with insulin dependence, they need to know how much insulin they need to inject in the body to maintain this level, depending on the glucose level they have in the past and the amount of food and other particular terms they are having. So in this work, the objective is to create a methodology to obtain accurate predictions applying genetic programming based on the input variables, what I referred in the past slide. That is, knowing the glucose level measured by a continuous glucose monitoring system, the amount of carbohydrates estimated by the patient, and knowing the insulin to know what is the level of glucose. Or in other words, we want to know how much insulin we need to put to maintain the glucose level control. So the methodology we use here is to first, of course, we need to collect the data for preparing our models. Then we put this data on a database and we make a data preprocessing and curation process. We divide the data in several parts. Here in this problem, we apply a division in terms of 6 hours, but we are now working on division of the data also in 6 hours, but starting from the intakes. With the division of the data, we perform a clustering of the data to prepare different models. And we also apply a data augmentation phase in order to improve the quality of the training. With this, we train different models for different clusters. We apply a phase of selection and constructing an ensemble model. And once we have the ensemble model, of course, we can start the predictions. We can see here clustering processed by Camin's typical technique, where the objective is to obtain models for the particular trend. The problem also is the additional problem we find is that we need to obtain a good cluster, because otherwise we are going to confuse somehow the predictor. But for example, in this typical clustering process, we can see that different clusters are quite closely following the patterns of the group. So the final objective, as I told, is to discover glucose profiles that identify similar situations in patients with diabetes mellitus type 1 and incorporate this knowledge to the model. In this block, we obtain, we process the clustering algorithm to this divided data, and we obtain blocks of data where we can apply the model. With it, we process the data to obtain data augmentation. We perform cross validation of the modeling process using evolutionary computation techniques, in this case genetic programming, and then we made an assembler of the model and obtain the predictor. In order to selection the best model, we use the archaic information criterion, which measures the relative quality of the model based on the entropy of the information. The idea is to select those models that give us the best prediction using the less possible variables, the less number of variables. So if we have two models with the same, let's say, similar prediction quality, we select the model, the simpler model. And in order to measure the quality of the prediction, we are using the Parkes error grid, which is a typical grid used in glucose predictions for measure the quality of the misprediction. The idea is that we divide the graph in several zones, and as the zones go out from A and B, we have more dangerous prediction. The predictions on C zone are worse or more dangerous than prediction B, and so on. The idea is that when we make a prediction that implies a change in the treatment of the patient, this is dangerous since, for instance, we are predicting a very high value, which means that the patient, the treatment will be to put some insulin. But in reality, the actual value is a low value, and that means that if we put this recommendation of insulin on the body, we are going to have an hypoglycemia. So at in zone E falls those predictions. For instance, where we make a prediction of 400 milligrams, and on the actual value we have a low value, which means that we are going to change the treatment which is recommended for the situation. So having that in mind, what we want is to minimize the prediction on the zones C, D, and E, and to maximize the prediction on zones A and B. So let's go using this Parks error grid to the solutions to the experimental results. Here we are showing the timing range for different prediction. So we are seeing here the results of the clustering algorithm, and we obtain different color agrupations of the values. For instance, in the first patient, or for different patients, here we are showing 1, 2, 3, 4, and 5 patients. Let's go to the top of the table, where we can see is that for the patient 1, days Monday, Wednesday, Saturday, and Tuesday and Thursday, are similar in behavior for this patient. So we found different patterns where we can say that the treatment for days are similar, and inside of this day we also found similarities for the nights. For example, group O and 1 are for the nights, and behaviors different for the other parts of the day. And for example, on Fridays, the last of the fourth row, we see that this patient had two patterns to the Friday, one for the blocks 0 and 5, which means that probably this patient go to bed later on Friday, which could be a good explanation. And with this, we made so we divide this in several groups, and instead of making a model for all the day, we make a model for this specific part. We use the blocks that falls on each cluster, and with that we made the modeling process. So if we do that, we can see that the predictions are improving when compared with the prediction of only modeling for all the day. Here we can see the ratio of the model with better prediction, that is with higher values in zone A and B for different clusters of the data. Dark gray segments indicates that the best prediction is made for the cluster process, that is the shade with a genetic programming process, while light gray means that a better model from genetic programming without the clustering. As we can see, depending on the patient, but for most of them, we have better predictions for those with clustering process. If we look at the different time horizons in this block, we can see that especially for higher time horizons of the time, we obtain also better prediction. This is can be seen better here in this slide. Here we can see the prediction for different time horizons, starting from 30, 60, 90, 120, 150, and 180. And as we can see, the behavior, this is similar for all the patients, and just highlighting the general process or the general behavior. The GP models with the shade, that is with the clustering process, obtain better prediction for most of the horizons, where green values indicate better solution for this. So this is the experimental results. We can conclude that using a clustering techniques improve the quality of the prediction of the genetic programming modeling. Concluding the work, we can see that significant differences with a p-value lower than 5% is associated with glucose profiles classified using the independent variable state of the width and tail slot. So we obtain different patterns with statistically significance. Then the accuracy of prediction with model created with the genetic programming is better for shorter time horizon, and gradually it gets worse as the time horizon increase from 30 to 240 minutes, which means that the clustering process improves the prediction of the genetic programming. Then in general, when using classified glucose values in model, with the accuracy of the prediction of the glucose improves in comparison with those models created with the original data sets. And the significant difference found in the classification process can be useful also for correct and improve the habits or therapies in patients more out of, or even out of this modeling process. The classification and the prediction of the patterns can help the physician to improve the quality. Finally, the results obtained will facilitate mathematical modeling of glucose and can be used for the creation of an individual classifier for each patient. The future goal will use the time series into different meals of the day, and we cluster using K-means and other techniques. We also use this information for creating models with grammatical evolution. The complete general method will be applied for all the general process. Finally, let me finish thanking for the authorities that are supporting this research. First, the Fundación Eugenio Rodríguez Pascual, which is a private foundation in Spain, which helped us with an important amount of money for getting the devices for measure the glucose, and also some computing resources. Then to the Ministry of Economy and Industry in Spain, and the community of Madrid, the regional government of Madrid, with the federal grants, with two projects that are supporting also this project. Well, thank you very much, and I open for questions.